From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
I think what's interesting is now having been in the industry for a fairly long-ish time, seeing that, seeing the same problems that the early adopters are going through now, kind of more mass adopt the followers, fast followers or whatever they're called, are kind of going through, and they're the same problems. And so I think, but we've learned a lot through what the early adopters have gone through to kind of accelerate solving those problems for the more mass market customers. But I think, it's so common that still to this day, in the end, almost 2022, where somebody is just like, hey, I designed this part in CAD, can you just 3D print it and make it better and cheaper? And it's like that education to get someone to realize, hey, it actually starts from the design. You're not just going to take this step file that you have that was meant for a machine to be machined out of a brick of aluminum, 7000 series aluminum. You're not just going to take the step file and magically give it to the guy the person who's in front of a 3D printer, and they're just going to magically 3D print it, and it's going to save the world. And
that was Brad Rothenberg. Brad is the CEO and founder of nTopology, a startup developing Generative-Functional CAD software based in New York City. Prior to founding nTopology, Bradley graduated with honors studying architecture at Pratt University in Brooklyn, New York, and Brad has been developing computational design tools for advanced manufacturing for over a decade. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. Brad, thanks so much for joining the show today. I'm excited for the conversation and hearing your career story and what you're doing at nTopology. So let's begin like we do with most of the episodes, with kind of some cameos from my screaming kids in the background. Where are you from originally? What put you down the path that led you to nTopology and additive manufacturing?
Well, yeah, thanks, Mike, and thanks for having me on the show today. And I definitely appreciate the screaming kids. I have a cat with me in the podcast as well, although I don't know if she'll scream during the podcast. But
hopefully not.
No, hopefully not. Right. But so I grew up in Connecticut, about 45 minutes outside of New York City, close to where GE's headquarters used to be, and there's a lot of engineering in that area. Sikorsky is there. They make subs also, kind of further deeper into Connecticut, but helicopter subs. GE, there's a lot of space tech. It was around the time when the Hubble telescope went into space, and they needed to put glasses on the Hubble telescope because its vision wasn't 2020. And so I had a CAD teacher in high school. We had CAD in high school, and I had a CAD teacher who I was really excited by, because he was yeah, I worked on helping to put glasses on the Hubble Space Telescope. And I thought that was really interesting. I was always interested in model rocketry, aircraft. I was obsessed with SR-71 Blackbird and stuff like that. And I was also into computers and programming, and I would build websites and stuff. This was in the, I was born in 85. So this was in the 90s and stuff like that. And fast forward to college, I studied architecture because I liked this. There was more software choices. There was computational design was a term in architecture. It wasn't a term yet in engineering. And I was really interested in what are the new possibilities the computer could allow us to build and make. And, you combine that at the same time, manufacturing is going through this massive change, massive, quote unquote, revolution, transition to digital manufacturing, things like 3D printing, et cetera, which is really kind of pushing the envelope of what we can make and allowing us to make some incredible new shapes and new things and, new materials. And the design, I was always frustrated by the design tools. They were, CAD being based on drawing and drafting. It made you have to think through solving engineering problems through how do you draw these. And I was like, okay, the computer is a new tool. Can't we use the computer in a new way to to solve engineering problems, like full stop. It's not about so much how to draw things anymore, right? We can make things directly from a 3D solid. Let's generate the 3D solid as the solution of an engineering problem. So like if you look at like really good, good engineering is based on really good design, and good design solves problems and solves engineering problems. And again, I became obsessed with that and obsessed with what the potential and possibility of using computers to better solve engineering problems. So after school, worked in architecture for a little bit, writing software for architects, and then moved into doing got obsessed with 3D printing and trying to engineer fabrics and textiles, and working with some of the footwear companies and stuff like that. And then started nTop because I realized, hey, there actually is no software that can solve these type of problems. And that was the origin of nTop. And fast forward another 5-6 years, and here we are today. We have this product that's used across aerospace and defense, automotive, medical device, consumer by some of the biggest companies out there. And, solving really hard engineering problems. They're not using nTop to replace CAD. It's not at all about trying to make a new CAD. It's about, okay, what are the engineering problems that exist in a company that's making airplanes, or that's making heat exchangers, or that's making cars, electric cars, or medical devices that get implanted into people's bodies. And what are the engineering problems they need to solve? Is it about making a patient-specific device that fits in somebody's body? Is it about making a plane lighter weight? Is it about making a better heat exchanger? And really targeting the software at solving those problems. And we do that with having really differentiated technology. The core problem that I saw with CAD is it wasn't scalable, being built on top of tech engineered in the late 70s, early 80s for drawing and drafting.
That's awesome. And so do you remember kind of with your CAD teacher that you had in school early on, what was the first thing that you designed digitally? That's
Good
going
question.
way back. But
so what it was? We had to draw mechanical parts, and there was 20 of them, and the teacher would lay them out on a desk and grade you based on those mechanical parts. And normally it would take you the whole semester to draw all 20 of them in CAD. And we had I'm going to date myself, but we had a pen plotter. So this is a machine that actually looks like a 3D printer, except it only moves in 2 axes. So, imagine you have a 3D printer that has an x-axis, a y-axis, and a z-axis. A pen plotter really just has x and y, and it picks up a pen, and you had different pens that were thick to thin. And the machine would move the paper in one axis and the pen in another. And from that, you can make a drawing. And then you would take that drawing and put it in a blueprint machine. It would make more blueprints from that, or it would duplicate it. And I would finish I would get through all the 20 mechanical parts in a month. And then I'd have however many months were in a semester or whatever it was left to just play around. And so I started, I was okay, I'll design a boat. And I got this software, Multisurf, which was a NURB surface modeling tool, and made a boat. And I was okay, I'm kind of bored of this now. What else can you do? Oh, this was back in the day. I think it was AutoCAD RT12 had this functional programming language called AutoLisp. So you could write little plugins and algorithms which would generate the drawing. So I was okay, I'm going to learn to code and write these plugins that would make these drawings that would drive the machine to make stuff. So it was these things probably looked like early nTop things, trying to make a lattice that could be drawn or something like that. And in doing that, I realized that these programs, they can be hacked, they can be built on top of, they can be extended. And in school, by hacking and building and extending CAD programs, I realized that the core problem was actually, you can't just hack on top of the core modeling tech that CAD is based on to solve engineering problems. There needs to be a new base architecture. And that's really what the origins of nTop came from. And literally the word nTop, or nTopology, means any topology. And topology is the field of math that we use to understand shape. So the idea is, okay, we can make any shape. If you could have any topology, you could generate any shape.
So talk a little bit about those early days, right? You have this idea, you've identified the need in the industry, but then it's still kind of a few steps. You made it sound so simple and kind of your overarching description of kind of where you are today, but kind of describe some of those early steps towards building your own company and building a product out to and finding customers.
So it's very simple in hindsight, right? Because it's easy to look back and kind of formulate the narrative. But the reality is it's like chaos. It's like chaos of trying to hack some code together, then going on site with a customer, whether it was like, going down to Under Armour in Baltimore, or like going out west to Portland to some of the other shoe manufacturers, or like going out to AFRL, the Air Force Research Lab, and like literally like sleeping on the floor in front of a metal 3D printer, trying to get the machine to print a satellite, like, and then rehacking code. It was like chaos. And in those years of chaos, it was like figuring out, okay, there's real problems that, whether it was at like Lockheed, for example, or like Stryker doing medical devices, like there's real problems that these companies have that the current set of tools can't solve and they'll never solve. And there's more and more of those problems coming about. And again, it was like, or maybe like organized chaos, because like the vision was there in terms of, manufacturing's going through this big shift, creating all these new engineering problems that the current set of tools just were never built to solve. So there's room for a new entry in the market. But like really figuring out what the solution was. Like it took us, we were looking at different data structures, whether it was like representing these lattices as beams, which worked for lattices, but not for other shapes, to like using voxel. Like this is kind of like techie stuff, but like voxels, which are basically little boxes in 3D to represent geometry, which doesn't really scale as you get bigger, becomes unnecessarily big, to really landing on the implicit model architecture, which is just pure math.
And so how do you, in those early days, like I'm always fascinated by kind of the startup journey, and you've got this product / idea that it's more than half baked. You have proof of concept, you have prototype, but how do you get some of those first early adopters to take a risk on you? Kind of what was were you people that you had known from your network? Were you kind of looking at specific types of problems and saying, hey, like I'm guessing Under Armour and Nike have these same problems, and so we're going to try and build something specific to that?
And it's about putting yourself out there and talking to people and finding the people that are willing and early adopters, right? Like we have another guest, but it's about finding the people that are willing and early adopters that will push the technology. And hopefully there's more people like that. And it's, sometimes there's a trap where you can like find somebody who's an early adopter that could, drive you the wrong direction per se, right? Like it might just end up being like a research project. And so I think what worked for us was really staying close to production components. So it was like, working closely with the people that were actually designing like tread. Like there's a person or a group or team at every footwear company that literally every single day someone sits down at the computer and is like, how can I make a tread pattern less slippery when someone runs? Or how do I make the best tread pattern for football? How do I make the best tread pattern for sprinters? And like that is close, like making sure that that's tied into production products and components, versus finding somebody who's like, oh, I just want to solve this math problem, etc. And sometimes that's not easy to differentiate. And I think that if I look back, it's about, in aircraft, staying close to the actual programs, not just like the pure. It's the difference between someone saying, hey, I want to make a piece of secondary structure a little bit lighter on an aircraft, to somebody saying like, hey, how can I just want to make some lattice.
Yep. Yeah. And so I like the comment you made of kind of putting yourself out there, and you just got to kind of have these conversations and see where they go. Because it's so much about this industry it's so diverse. I mean, the companies you listed are in footwear and medical and aerospace, different requirements, different materials, different processes, different regulations. Right. And so your brain must be spinning some days of the variety of types of projects and types of conversations that you see, but it all fits in the same idea that underlying, like, CAD can't do the job that it's being asked of. And so we want to build a tool to solve for some of those challenges.
Yeah, spot on.
So as kind of the company has grown and evolved, like, what I'm always curious from generally in additive, like this whole education spectrum, right? You have some very sophisticated users that you mentioned, some of your early adopters that like know the machines inside and out, know the technology, know the tools. But then there's this whole much larger market that is learning about the technology, getting kind of their feet in the door. Kind of, where do you generally like to kind of see your initial customers, or even today, like some of your customer base? Where do you mostly see them? Are they still sophisticated users, or are you kind of branching out and seeing more like just more educated folks across the industry adopt the technology? Where do you kind of see the adoption spectrum as it stands today?
So I think what's interesting is, like, now having been in the industry for a fairly long-ish time, like seeing that, seeing the same problems that the early adopters are going through now, kind of more mass adopt the followers, fast followers, or whatever they're called, are kind of going through, and they're the same problems. And so I think, but we've learned a lot through what the early adopters have gone through to kind of accelerate solving those problems for the more mass market customers. But I think, it's so common that still to this day, in the end, almost 2022, where somebody is just like, hey, I designed this part in CAD. Can you just 3D print it and make it better and cheaper? And it's like that education to get someone to realize, hey, it actually starts from the design. Like, you're not just going to take this step file that you have that was meant for a machine to be machined out of like a brick of aluminum, 7000 series aluminum. You're not just going to take the step file and magically give it to the guy the person who's in front of a 3D printer, and they're just going to like magically 3D print it, and it's going to like save the world and make us, not raise 4 degrees in Celsius in the next 100 years, and like, solve sustainability and make the aircraft faster, or the plane or the car drive further. Like, that still comes up today. Like, can you just 3D print this step file? Like, it'll be better, right? And it's like, no, it won't be better. It's going to be more expensive. It's going to be worse material properties. It's just going to be worse in every possible way. But it can be better if you start thinking about design around, like, thinking about, get back to good design, think from first principles. Here's the manufacturing technology. Here's the constraints around the manufacturing technology. Think about solving that problem, whether that's a heat exchanger, whether that's a piece of structure, whether that's some type of product, whether that's a medical implant that has to integrate with your bone. Think about how would you solve that problem with the constraints of 3D printing, and that will kind of free you to actually produce a better product that maybe is more efficient. I mean, we have customers now that are historically not the early adopters. They're not I think there was a statistic that Stryker was like shipping hundreds of thousands of 3D printed parts, right? Like, we're seeing medical device manufacturers that are like Stryker is an early adopter with the technology. We're seeing medical customers that are, let's say, quote unquote, new to 3D printing, that are, getting to market with products that are FDA certified relatively fast. Using our software, they can get to certification like in 2 weeks, 2 or 3 weeks from a design, when that could have taken months before. or like people that are designing heat exchangers, taking heat exchanger design time from like 60 hours to an hour and getting a heat exchanger that's like 50% more efficient, for example. And so there's several examples of these across the different application categories, but they're the companies that are getting there in terms of the higher performance, faster time to market, cost savings, are doing so by thinking through design from kind of first principles in terms of like, okay, how can we leverage the capabilities of this technology, whether it's a printer from Velo or EOS or Concept Laser, and what are the overhang angles that are possible? What are the material property range from the process? Do you post-process it? Does it cost more to post-process it? Maybe you design a part that doesn't have to be post-processed as much, so you save on cost, right? Like we're still working in a process where the material is orders of magnitude more expensive than a traditional manufacturing process, specifically in AM. On the flip side, we're also seeing applications in our software outside of just traditional additive manufacturing, in which I would kind of group as like advanced manufacturing. Like we're seeing tooling applications where people are making like cooling holes in tools where they're just arraying thousands of holes on a tool that get machined out, or building like structures that are machinable and working within the constraints of the manufacturing technology. I was going to say too, I have this theory that I'm working on, which is like the closer the design is to the manufacturing and the more feedback there is between, like literally in physical space, the closer that the design engineer and the manufacturing engineer and the part that comes out of the process is, the closer they are together, the quicker they can get to better performance. And I think like a good example of that is like the SpaceX factory, or like Joby Aviation, where they're essentially designing and building the majority of parts on their systems in one facility, and vertically integrated through design, or Tesla even. And you're seeing some amazing innovation where it's like, in Tesla, the batteries are part of the structure of the frame, right? And if you were thinking through the old way of manufacturing, you would have a battery supplier, you might design the frame, and you would call up your battery supplier and say, okay, deliver me batteries with these capabilities and these requirements. And then you as the OEM would like bolt the things together, and you design like a really good bolt pattern, you design a really lightweight frame, and you'd have whoever makes the batteries design the battery pack and the packaging, and you'd bolt them together and get an efficient battery pack and efficient frame. But that's not going to get you a car that drives faster. What's going to get you a car that drives faster is actually like some interesting design thinking where like, wait a second, these batteries have structural properties. It's not as good as the frame, but if we combine them with the frame, we can get rid of the packaging, we can get rid of bolting them together. And now we can get a lighter weight frame that integrates the batteries into them as the actual structure. And that to me is like really innovative thinking that only happens through this kind of like first principles approach to solving engineering problems.
You actually answered my what was going to be my next question, is kind of the idea of like from where you sit, kind of what are the common characteristics of teams that you see be successful in either adopting additive or kind of really using your software to get that better performance, better speed, lower cost, whatever it may be. So it sounds like it's the closeness, or like the physical kind of co-location of a lot of these.
So that's my theory, that it's like the co-location, but I think what it comes down to is like just thinking about what the actual engineering problem that you're trying to solve is. Not thinking about what is my current process today and how can I work within the confines of my process. Like just because we have a supply chain, if you were using a traditional supply chain way of thinking, you would never get the batteries integrated into the frame of the structure, right? Because you'd have a supplier and you'd have this like separation. But if the engineering problem that you're trying to solve is like make the lightest weight system for a car, period, like, you could say, okay, like another example is like, designing the housing of the motor. The motor gets hot also. You could say, hey, let's call up, heat exchanger supplier A and say, let's get a good heat exchanger. And then you could call up whatever company, like say Honeywell's making a heat exchanger, and you have Siemens that makes the motor and the case, and you have some other company that's like making the batteries, right? If you call each of them, you're going to get 3 different things that you have to bolt together and wire and do all this stuff to. If you're thinking about the design problem, you just want to make a better motor. That motor has heat that you need to remove from it. That motor needs to go fast and it needs to be powered, right? So how could you design a better motor? Like, could you integrate the heat exchanger into the actual motor itself? Can you integrate the batteries into the motor itself? Like, why think through having these separate things put together? And I think by having, like, one way to do that is have everybody in the same facility. Yeah. Now that might not be realistic, but I think like that's definitely one solution, because you have, engineers are good at solving problems. And I think it's, if you're forcing them to think through the way that we solve problems for traditional manufacturing, traditional supply chains are very mature as an industry. And so as an industry matures, it's natural that you build supply chains, you build out suppliers, and you decentralize stuff. But when markets are new and emerging, you kind of need this vertical integration to drive a lot of the innovation that eventually will get segregated. Oh, go ahead.
I think that's a great point. I mean, we've just seen over the last year or so, the amount of people that have come asked us about more out of necessity, like, hey, our supply chain is broken. It's like, we can't get X, Y, and Z part. And now we're looking at 3D printing as an option, but it's forcing people, like, from a different angle. It's like, hey, they've got a big problem. Like, they can't actually use the same supply chain thinking that they've been doing before, forcing them to explore other 3D printing technologies or advanced manufacturing, whether or not it's a good fit. But it's allowing them, you start to get some of those cost considerations in a more broad spectrum. It's like, hey, like, on paper, this is going to be more expensive part per part, but I can get it faster. I can get it more aerodynamic, whatever it may be. And so it's an interesting time, I think.
I mean, absolutely. And I think you're seeing a lot of startups that are hitting the market now that are like, hey, we're going to build a product. We're just going to like make a better product. And they vertically integrate from, like, if you look at Relativity Space, or so, I mean, SpaceX is a kind of perfect example of this, where again, they're delivering a rocket product and they're solving that from first principles. How can we engineer a rocket that's cheap to get into orbit, basically?
For sure. And so kind of taking kind of this conversation on teams and kind of building things out, like, what was your philosophy as you were starting to kind of build out nTop's team, and as you continue to grow, what do you have any kind of advice for both kind of people building their own teams, but also, like, what have you seen as kind of being successful in your organization? Like, are there any characteristics or things that you like to see when you're hiring new people?
Well, I mean, first it's like hire people that are better than you, at things. Like, I was writing the code early on at nTop, and then I hired people that were much better than me at that. And I haven't touched the code in years, or a couple, like, in a couple of years. I still use the product, which is fun. But I think the last 18 months has kind of changed the game in terms of, like, all of this stuff around, do we go fully remote? Do we go hybrid? Do we force everybody back into the office, et cetera? I think one of the big learnings is that, at least from what we've seen, is like the office is really important as a place to work and as a place for people to collaborate and work together. Like, I don't think the best work, especially when you're doing something new that hasn't been done before, like, getting people together to solve problems is better than having people apart working in a kind of, not real-time way with each other. But that's kind of an ongoing, it'll be interesting to see the next year in terms of hiring and scaling.
Sure.
But there's different phases of a company as you scale up, and,
And I think one of the themes of this podcast as a whole is kind of showcasing different kind of facets of the 3D printing and manufacturing space. I would say kind of what, even today, like what percentage of people that come into your organization, like were familiar with 3D printing before kind of coming in? Was it early on, like everyone was like, hey, gung ho about 3D printing design, or like we've interviewed I've interviewed about 70 people at this point. I would say 90% of them kind of stumbled into 3D printing in some way. It's like, hey, like,
so like 3D printing early on was an industry where people that like didn't fit in other places kind of ended up, like it was like the people that were like, you know, the quote unquote rebels of their company were like the ones looking at 3D printing they were like, you know, let's change the game up. You know, I think especially early before my time, the people that I work with and talk with every day that were, you know, building 3D printed pieces of aircraft structure, like in the 90s, like they were pushing the limits of what was possible. And they were up against gigantic walls of like friction in the organization because the processes weren't proven out. They were in organizations that were built and optimized around the legacy generation way of working. And these were people that were pushing the limits. And, you know, for us early on, I would say actually, like, you know, everybody has heard of 3D printing now. Everybody knows the term, especially like in, you know, when nTop started, it was right on the tail end where, you know, MakerBot was coming to market. And, you know, this notion was that you were going to have a 3D printer in your garage and everything was going to be made out of a 3D printer. And in fact, like when I was raising money early on for nTop, you know, like 95% of the investors that I talked to, well, one, they all said no, but they said, hey, like you're a really interesting founder. Like if you just focused on a product, you know, these are going to be 3D printed products in people's garages. And I'm like, it's not really where the technology is going. Like this is going to be used in the manufacturing setting. It's going to change the way products are developed, but consumers, they're not going to really care that much whether they're buying something that's 3D printed or not 3D printed. Like it doesn't really matter. What matters is getting a better iPhone, getting a better computer, getting a better car, getting a better plane, right? That's what people tend to care about. Like you don't buy an iPhone and you're like, oh my God, this iPhone is machined out of a single brick of aluminum. At least the majority of people don't. There might be some people that listen to your podcast that do buy iPhones because of that. But just know, for those people that do buy a phone for that, you're not like the majority of customers that are out there. And so, but I guess that back to your question, like how many people are familiar with 3D printing? I would say everybody is familiar with it. They know the term, they know it's new manufacturing, they know it's going to change the game. But I think very few people really like understand the applications for it, understand it as, why is this, you know, just it's another way of making products. And, you know, there's always new ways of making things. Like we as humanity are constantly developing new ways of making things. And sometimes those new ways of making things have a major impact on the world that we live in, and other times they don't. And this, you know, 3D printing specifically is kind of a new field of the way of making stuff, right? You're not starting from a brick of material and carving away at it. You know, you're really developing the material and the shape at the same time. And that gives engineers and designers new ways, new capabilities. And those capabilities, you know, the processes that you use to get the most out of, you know, machined bricks of material are different than the processes that you need to get the best capabilities out of building material and shape at the same time. And so that is what people learn as they're at nTop, and that's kind of what's exciting about the industry. And that's also what's so exciting about where we are, because, like, you know, we're really fueling this new generation of products that are being built.
Absolutely.
In the background, I know, right? We're like the tool maker. By the way, you could hear my cat is like going crazy in the apartment. She's getting very excited about 3D printing.
Yeah, my kids are down for nap, so it should be quiet now. So I got kind of two questions left. So the first one is, For someone new getting into 3D printing, additive manufacturing, certainly on the design side, what piece of advice would you give them to kind of help move their career ahead, or if they're even changing industries or changing roles in their company?
I mean, I would just think about why are you excited about 3D printing?
Mm-hmm.
What excites you about would you get excited about 5-axis machining in the same way?
Yeah.
Right. I think again, it comes down to what are the types of engineer, what are the problems that you're interested in solving, and 3D printing might be one approach, machining might be another approach. And I think again, it comes down to thinking about what are those problems. If you're really hey, I'm really interested in 3D printing and solving 3D printing problems, maybe it makes sense to go work for a company that makes 3D printers and solve, there's so many unsolved problems in 3D printing, getting the laser power to put consistent power into metal so that, the metal melts together without any defects. There's all sorts of hard problems to solve with that to make this, figure out how to solve the problem of making metal powder for 3D printers 10 times cheaper or 100 times cheaper, right? If the metal powder was 100 times cheaper, 3D printing, the applications that we could use powder-based 3D printing with metals for laser powder bed fusion or binder jet even, would unlock a whole nother set of applications that because of the price point.
Mm-hmm. Awesome. And so the last question is kind of, what are you excited for kind of in terms of yourself, kind of the industry, the company, kind of going forward into 2022?
I mean, I think going into 2022, I'm excited about one, real production applications, seeing parts actually fly, seeing parts on cars, seeing parts in shoes, seeing more products in people's, saving people's lives or protecting people even. I mean, the thing that motivates me the most is the products that are designed in our software today and the potential products that will be designed in our software tomorrow. And so that's the thing that it excites me the most.
Awesome. Well, I appreciate the time today. Thanks so much for joining the show, and we'll see you in person one of these days too.
Awesome. Thanks so much, Mike. And it's fun to chat, and have a good rest of the week.